Hi everyone, my name is Michael Lin. I'm a research scientist at MIT Media Lab City Science Center. On behalf of City Science Lab at Taipei Tech, I'm pleased to be here with you today to share some of our latest research developments. At the City Science, we believe design, technology, and policy must work hand in hand. None of them alone can solve the challenge cities are facing. And that is why the City Science Lab at Taipei Tech, we co-create with our sponsors and partners across all three. Our mission is simple but ambitious to build a better urban living condition through technology tools. So how do we actually do this? Let me show you the framework that we're using. Our work rests in three layers. At the base is a large spatial temporal database. This is a knowledge base that hosts open and proprietary government, public, and private data. The middle is supported by different AI modules, and we develop an agentic AI framework for cities. Think of it as a team of AI modules. The utility functions are the helpers, domain algorithms are the experts, and foundation models are the shared brain. At the top, our system does two things. It helps the city to see through urban analytics, and it helps city to act through urban robotics. Together, they form a loop, cities that see clearly and respond wisely. The spatial temporal database is our core infrastructure. We take messy city data, like points, line, polygon, rasters, and other types of data. We sample them into dense points, then turn these points into a hierarchical indexing system, and then put it in the hexagon cells. This way, every attribute could be stored, queried, and compared at any scale, from the city as a whole to neighborhood down to individual buildings. So using a web-based map platform, users can freely move across the map, switch between different data sets, locate specific areas, and then they can go to the areas that they're interested in exploring the details. The platform is designed for smooth, intuitive interactions, whether you are exploring a broader pattern or focusing on a specific details. You can also explore temporal layers, see how the city evolved over time. Once we have the structured data like this, the next question is, what can we do with it? Understanding how people move through the city provides a valuable insight for urban planning. When combining spatial temporal database with AI, we can simulate the movement of the entire cities. We began by modeling the virtual residents, generating their daily activities such as work, school, and shopping. We match this in the activities to real locations, route their trip by walking, transit, or driving, and then visualize the flow. So we call this platform a multimodal mobility simulator. And here I want to show you a demo of this multimodal simulator of Taipei. This is a digital twin of human behavior. The platform visualizes how people commute, where they go, work, and then where they buy a cup of coffee and return home. Each dot on the map represents a virtual residence. There are about 100,000 of residents being simulated at the same time, and you can watch the city breathe. It is a living digital twin that shows the urban movement across the whole city. If data analytics is how city sees, robotic is how city act. Over the past 3 years, we have built many different robots, both wheel robots and leg robots. Here you can see our dinosaur robot, a playful platform where we use to teach visual slant, learning the robot map and localize itself as it moves. This video shows a 12-degree freedom quadrobots powered by dynamic servos. It's a teaching platform for students to learn how to generate gates and schedule motions for four-legged robots. Here's a simulation to reality interactive panda, capable of mimicking animations designed in Unity. This platform bridges the gap between digital characters and physical robots. We've also developed simple LQR controllers that help the bipedal robots to stay balanced while walking on uneven terrains. And this is actually a collaboration with Professor Juan Oliveras from Guadalajara. In this video, showcasing the autonomous mission carried out by the Boston Dynamics Pod, we've developed additional mapping, localization, and path planning and perception algorithms for SPOT. The goal is to enable auto missions and fleet control for factory inspections. And we use the lab in Taipei as the testing ground. So using NVIDIA Universe, we're also creating a digital twin of our lab so the researchers can test multi-robot communication and coordinations in virtual environment before they carry out in the physical space. As you can see, the vehicles moves around in the videos. So this is NVIDIA Isaac Gym, a virtual physics simulator for robotic research. Robotic requires multidisciplinary collaboration. Students with computer science background could learn how to train a robot control policy in simulations. However, the students still need to work with mechanical engineers and electrical engineers. Together, they build a physical robot and deploy the controllers they design and fine-tune these controllers and test out the performance in real world. What excites me the most is watching the students realize they need each other. The coders will never touch a motor drive. The engineers will never train an AI policies. They discover that only working together they can make a robot walk. So this summer, Professor Juan Oliveras from Guadalajara spent 2 months with us. In his farewell note, he wrote, "The real taco isn't just what it is inside the tortilla. It's the story, the culture, and the friendship that we share." For me, this wasn't about working together or making tacos. It was about culture. Juan reminds us that the science and engineering are also about community and belonging. So during his time, Juan became a leader of our robotic team, guiding the development of a new open source robot we call the Pineapple. And we are planning to continue this collaboration across universities of Guadalajara, Carnegie Mellon, MIT, and Taipei. So this summer, we had the opportunity to receive students and researchers all around the world. We met in Taipei, we worked together, we share skills, stories, building systems together, and learn from one another. At its core, it's actually co-creation. This is a small community, but a global one. To support this co-creation, Ken and I are building something bigger. We call it the Learning Foundry for AI and Robotic. In short, it's also called the Learning Fair. We don't want to just teach. We want to create a platform, a repository, and a living lab. So it is a learning festival full of energy and exchange. The fair, it's also about education equity being fair to everyone. So FAIR is also our guiding principles. Fair, we propose free access, full scholarship, and open materials to the world. A represents AI-driven learning, an AI tutor, and a knowledge graph that guides you step by step. And I includes for inclusive peers, matching learners across the city so you can grow with the people at your level. And then lastly, R, reverse admission. Instead of waiting for applications, we scout our standout learners, invite them to programs like MIT. Although Taipei and Guadalajara are far apart with different language and different culture, we now share a platform, a network, and friendship. My hope is that in the future, every city in our network will learn and build together, and this is the promise of the Learning Fair. Thank you.